assign them with constants. Not all groundings are presented here, because there are some groundings that really don't make much sense. For example, another grounding would be Frank to be friend with himself, but we omitted that ground for simplicity. So the evidence already gives us some truth values, which we underline. And the truth values of these predicates, we already know them. For example, we know that Frank smokes, so its negation, it's false. And we cannot say right now anything about whether Frank has cancer or not. So we label it with unknown. We do know that Gary does not smoke, so the negation of a negation is true. And again, we don't know anything about this. And so forth with these other two rules. Here, we don't know whether Bob smokes or not, and we don't know whether he has cancer or not. And well, also here we know that this one is false, false. We don't know anything about Bob smoking. This one is false, false. And we don't know, again, anything about the smoking. So as you can see, some of these formulas are already solved, because this is an OR operator. So for example, this formula here already has true, so it really doesn't matter which value we give here, the formula is true. The same applies here. We have a true and we have a true. It doesn't matter the value of the unknowns. Here there is nothing we can really say about it because both are unknown. And here all we have are false and unknown. So we may need to make some of these unknowns true to satisfy the formula. However, we have a problem, as you can see here. This formula requires to be true that the negation of Bob smoking has to be true. But at the same time, here we have that the positive of Bob smoking has to be true. So here we have a contradiction. We cannot make them both true and satisfy both formulas. So what do we do? Well, the MLN then enters a search phase where it tries to give the best assignment to the truth values of these predicates. And what it does when it finds a conflict is that it looks into the weight of the formulas. Here we can see that this formula weights less than this other formula. So what the MLN is going to do is that it's going to satisfy the formula with the greater weight. Thus, it makes that Bob smokes is true, and well, that makes this formula false. It would remain unsatisfied, and this other formula would be the negation, so it's false. And to make the formula true, we make that Bob has cancer, unfortunately for him. So this was a small example. Now I'm going to tell you more in detail about this process, the inference process. As you could see, it was divided in two steps, grounding and search. And as I said, grounding enumerates all the assignments to the variables in the formulas. Once the formulas are grounded, you can see them that they represent a Markov random field, where each variable is unknown. Here we have an example of what a Markov random field is. Here we have the nodes, the different nodes, and each formula creates a hyperedge. Here, for example, we have the formula that Bob smokes and Bob has cancer. It's joined on an edge, and the other ones are also joined on an edge. Well, here the Markov random field is completely, well, almost very connected, very well connected, but the idea is that it can be partitioned. We are going to see later how, and with this partitioning of the Markov random field, we search for the most likely word of the MLN, which we can see that this assignment to the truth values of the variable of the grounded predicates can be seen as a satisfiability problem or an optimization problem. But These weights and clauses can also be learned. For weight learning, we need to first ground the formulas we have, and then we need to solve an optimization problem. This optimization problem attempts to find the optimum value for the weights. And well, an important characteristic of this optimization problem is that its parameters are adapted through sampling, which is a process similar to set solving, and also very time-consuming, as we're going to see later. And clauses can be learned with inductive logic programming. The idea is to use positive and negative examples from the knowledge base. The basic idea of this algorithm is that candidate clauses are proposed, evaluated, and just stop once you have found good clauses. But it's a very time-consuming process. Well, there are several applications in a great array of domains for MLNs. For example, semantic role labeling. If we have a sentence like Mary sold the book to John, the idea is to try to classify each word on the sentence according to its most likely meaning, to say that it's a word, a predicate, the predicate of the sentence, a verb, etc. And they have also been used for refining Wikipedia's infobox ontologies. Infoboxes are the boxes that are usually found on the right side of Wikipedia articles that have some resume of the information. And for example, the problem here is that some infoboxes are created by the users. They don't have like a formal definition. So one user could write birthplace for one article, and another one could write city of birth for another one. And well, for us, we can see that it is the same, but for a computer, it would be impossible to know that both are the same. So the idea of this autonomous system is to teach the computer that birthplace and city of birth are the same, and several words have the same meaning, even though they are written in a different way. Well, here we can see all the MLN processing step, the inference step, requires learning, reading the MLN, the grounding process, which we accelerate with GPUs, the partitioning of the Markov random field, which is a task left to the CPU, then the search step, which is both a CPU and a GPU task. They both work together to solve the problem. Finally, we display the results. For close learning, is the same. With the ILP, we read the data, we propose new clauses, we evaluate them, which is a parallel process on the GPU. If we have already if we don't have good clauses, then we propose new clauses. If not, we display the clauses that we found. On weight learning, we also need to ground with the GPU. We propose an initial value for the weights, and then we optimize this value, adapting the parameters of the optimization algorithm to a sampling method, which is similar to SAT. It's actually called MC-SAT. And well, once we have found good weights, we display it. So what is the problem of MLNs? Well, the processing of an MLN is quite complex. It can take hours or days to produce the results we want. And then when it produces them, those results may not be optimal, may be room for a lot of improvement on them. So several systems have tried to take advantage of several techniques like multi-core parallelism and lifted inference. Unfortunately, the processing time is still very high. So our hypothesis is that MLN processing can be accelerated, and also the solutions improved using many-core massive parallelism. And this can be achieved using graphics processing units, which are high-performance many-core processors capable of very high computation and data properties. Well, well, the objectives of this work was to design, implement, and evaluate a GPU-based platform for MLM processing. And from there, we had several specific objectives, like create parallel algorithms for all the steps of MLM processing, to describe the designs and approaches we used, create 2 MLM platforms, ground using our own data log engine for GPUs, which I'm going to explain later. Also create a GPU library to solve this satisfiability problem and the sampling problem, and adapt an existing ILP system to handle cloth learning in first order logic. Then we tested our platform with several applications and analyzed our algorithms for possible future parallel improvements. Related to MLMs, the most important works are the systems that process them. So there are several systems. The first one was Alchemy. It was created by Pedro Domingos, the creator of MLMs, and it doesn't have any kind of parallelism. Then the BIST followed with a different approach. Alchemy was, the search approach was based on SAT, the BIST is based on optimization. And the authors propose that you can have parallelism through the modularity of its components, but it actually doesn't have any parallelism per se. Then came Toffee, which tried to improve upon Alchemy, so it follows the same approach, and it uses multicores on the search phase to parallelize the MLM processing. Then came the latest CPU system, which is Rocket, which is based on optimization, and this one tries to do most of the phases on multicores. And then our systems one is based on Toffee and based also on the satisfiability problem. And it uses GPUs for the most time-consuming tasks, and also uses multicores on the search along with the GPUs. So both GPU and multicores are used together to solve the problem on the search phase. And then our other system is Rocket, is based on Rocket. It is based on the optimization, on solving an optimization problem. And it uses the GPUs for the grounding. For the search, it uses the multicores, not the GPU. So what are GPUs? Well, as I said, they are high-performance many-core processors. You can see them as single instruction, multiple data machines. There are several processing elements, the cores. All these cores run the same function, which is called kernel. But the thing is that this function is run on distinct data items, each core. And well, they have a wide array of applications, and they can be programmed mainly in these 2 languages, but the one we are using is called CUDA. Here we have the architecture of the GPU. Each thread has its own local memory that uses for variables and its own stack. Then these threads are grouped into blocks, each block having its own shared memory that can share with all the threads in its own block. And these blocks are joined together in a grid. This grid has several blocks which can be set to several configurations depending on the GPU. And these blocks share the global memory. Any thread from any of these blocks can access the global memory. What are some things to consider about GPUs? Well, we should always try to do all the data handling in bulk, to move data from the GPU to the GPU in bulk, or from the CPU to the GPU in bulk. We must also be careful with the limited amount of memory. If we run out of memory, then our application cannot continue. We should try to use all the resources of the GPU, not only a few cores. It's not efficient. And we should try not to use sentences that cause the threads to follow a different execution path. So if and while instructions should be avoided as much as possible. Some of the things that we can do to further optimize a GPU program are concurrent copies. That is, we overlap the copy of data with the processing on the GPU. We should try to have threads that are continuous, access continuous memory locations. That is thread 1 to access location 1 in memory, thread 2 to access location 2 in memory. And we should try to use shared memory as much as possible, because shared memory is much faster than the global GPU memory. And, well, GPUs can also interact with the CPU. One important thing to consider is that the communication between these two components is very time consuming. We should try to avoid sending data to the GPU as much as possible. They can work together to solve a problem. While the GPU is processing part of the data, the CPU can also be processing another part of the data. And also, it's also important to decide which hardware is better for the task. For small tasks, it's better to just leave the data on the CPU and process it, and for the GPU and big task to be left to the GPU. Now, to finish the introduction, just a small slide about optimization on the MLNs. Well, map inference can be seen as an optimization problem, a linear programming problem. And, well, fortunately, the feasible region of this problem is a convex polytope that really helps with the optimization algorithm. The clauses and atoms can be converted to variables and formulas, as I'm going to show you in this example. Well, I think I'm first going to show you. You see here we have some clauses. Each one has its own weight, positive weight, negative weight, and infinite weight. Infinite weight means that this formula is not probabilistic. It has to be handled as a first-order logic formula, so it cannot be broken. And so the idea is that for each of these clauses that doesn't have infinite weight, we define a variable, and we assign this weight to the variable. So we place C1 to this clause, and assign its weight to it. Then C2 and its weight to it. And then we put the restrictions to the problem. The idea is that those who are positive here, and then those who are negative, joined with the plus sign. You put 1 minus the variable. And then if the weight of the clause is positive, then you just put the variable of the clause, C1, which has to be greater than or equal than the variable. And for negatives, it's the same. We put, if it's in negation, we put minus 1 minus the variable. If it's possible, we put the variable. And now here we change the inequality. We say that this clause has to be less than or equal to twice the variable. Finally, the infinite weight has to be the same, and has to be greater than or equal to 1. Now, why do we do this? If we want to maximize this formula, then the most logical result would be to put 1 here and to put 0 here, right? Because this one reduces the maximum, so it has to be 0, so that this one is eliminated, and with 1 we have the rated value that can be achieved here. So to solve this inequality, this one is equal to 1, and any of this, if this variable is, say, equal to 1, then we have solved this inequality, right? So now this inequality is 0, and so we have to make sure that none of these variables are greater than 0. So x2 has to be 0 to satisfy this inequality, and x1 has to be 1. And then the inequality is satisfied, and we have also, in terms of MLN processing, it means that we have satisfied this clause. And this one is always satisfied because it has to be 1, so one of these ones has to be at least 1. For example, if we make this one 1, then we have satisfied the inequality. And by doing this, we have satisfied all 3 formulas, and we have the solution to our MLN problem in terms of an optimization problem. Well, also weight learning is another optimization problem. The idea is to maximize a formula called log likelihood, the conditional log likelihood, which has some nice characteristics for the algorithms because it's twice differentiable and convex. And this formula and its derivatives require that we know the number of times a clause, given the evidence, is true. And such information is obtained by sampling, which I'm going to explain later. And it has to be recomputed each time we propose a new weight vector with the algorithm. Well, now I'm going to pass to the core components of our formula, of our MLN systems. The first core component of our MLN systems is data. We use it to grounding. And it's a language based on first order logic. It has many rules which are easier to show you with an example. Here we have a very simple example of who the idea is using this rule to find who the grandfather of someone is, given who are his father and the father of his father. And so we have some evidence that the father of Harry is John and the father of John is David. Then we ask a query that we want to know who is the grandfather of Harry. And what we do is that we ground. We give values to the variables. We put John, David, Harry, John, and we find that the grandfather of Harry is David. And that is how Datalog works, and we have our own implementation for GPU called GPU Datalog. Its latest version has already over 7,000 lines of both C code and CUDA code. Some important concepts to consider about this is that it is based on relational algebra operators, so selection, join, projection. It has some additional operators and some other auxiliary operators. It can be used in a wide array of applications. Normal Datalog has been used for all these applications. It has several optimizations that has been developed by us, particularly partitioning, which is a very important one that I'm going to explain next. There are some issues that need to be considered. For example, string handling for the GPU is it's a complex matter because strings don't have a common size. They can be any size, so it is difficult for the GPU to handle strings as easily as it handles numbers. And usually for these operations, selection, join, you don't know what the size of the result is going to be beforehand. So you cannot easily assign memory to the result and beat up. GPU Datalog was developed during my master's thesis, but now has been it has some new additions and optimizations. For example, the negation, which is based on the set difference, arithmetics, some summation, multiplication, etc. It also has aggregation and its related operations, average, counting, summation, which is very similar to the group by in SQL. Also all the comparison operators, which has also been improved from its original version, and an interface to communicate with Postgres and MySQL. And now about the partitioning scheme, it is very important because it allows us to handle data that exceeds the amount of memory on the GPU, and it would also allow us to have a future simultaneous multi-GPU processing, maybe on a cluster of heterogeneous GPUs. The idea is to partition the data in the CPU, then load the partition and process it in the GPU, sending back the results and loading the next partition. To do this, the size of the partition is very important because if we choose too small partition, then performance is affected because we are loading and unloading a lot of data. And too large, and the result of the operation may not fit in memory. Right now, we have some dynamically adapted sizes based on the results of previous partition. So the idea is that if a result is not going to fit on its buffer, then the size of the future partitions is decreased. And if a considerable amount of memory is left free on the result buffer after an operation is completed, then the size on the partition for for the next processing of the rule is increased. Now about the satisfiability problem, the idea is to find the truth values to all the variables that satisfy all the formulas. It's not always possible to satisfy all the formulas, as we can see here. We cannot satisfy, this one can be satisfied, but here, for example, we cannot satisfy all of them, because here we need A and B to be positive, well, either of them to solve this problem, but here we are asked that both of them have to be negative. So, and that is what I showed you from the smoker examples, and also the idea of max worksat, that we will try to satisfy those formulas with a greater weight. So we will try to satisfy not A and not B, and leave A or B unsatisfied. Well, our infrastructure to solve this satisfiability problem is a library called GPU SATlib, which is based on max worksat. The idea of max worksat is to start from an initial solution and flip, that is, change from true to false or from false to true, the truth values of the variables found in formulas that are not yet satisfied. The decision of which atom is to be flipped can be done at random or specifically to satisfy as many formulas as possible. This algorithm can be extended to perform the sampling problem that we showed you for weight learning. And this algorithm, this extension is called SampleSat, and the idea is to sample around the solutions proposed by max worksat by allowing any variable, not only those of unsatisfied clauses, to be flipped. And how we parallelize these algorithms on the GPU? Well, instead of flipping one atom at each time, as the CPU does, we try to flip multiple atoms at the same time and compute all the results of these flips. And, well, this composes our library. It has around 800 lines of C and code. And now for ILP, we try to learn or refine formulas with training data and positive and negative examples. It has 200 lines of C and prologue code. And the idea is that at each iteration we propose a new formula and we evaluate to determine how many examples it covers. The problem is that the number of possible formulas that can be proposed is very large. The search space grows very quickly. And we incorporated GPU data log on an ILP system called Alep, which uses Prolog, JAP Prolog. And well, the idea is to accelerate the slowest pace of this problem, which is clause evaluation, computing the coverage of formulas, how many positive and negative examples each formula covers. And well, right now our system works for first order logic formulas only, but it could be modified to handle MLM formulas by modifying the coverage function that is currently used. And here we have the sequence diagram of how this system works. We start with JAP Prolog, JAP starts Alep. We read the data set and we search for a new rule. We compile the rule in a representation that is easy to understand for the GPU. We compute the coverage using our GPU data log engine. We have the set of positive and negative examples. And we evaluate if we can do better. Then we search for another rule, or otherwise we finish and show what rules we found. Well, those are the core components of our platforms. And now I am going to talk about the platforms themselves. The main component, our first platform is GPU Toffee. Its main components are the Toffee MLN system, Postgres SQL, JAP Prolog, GPU Datalog, and our GPU SATlib. It has some, added some 600 lines of Java and C code to the Toffee implementation. Toffee is in charge of doing most of the pre-processing of reading the rules, and Postgres handles the data input-output between Toffee and the GPU data. The grounding process is performed with GPU data log. It translates the MLNs to data log, while JAP serving as the bridge between Toffee and GPU data log. Once the MLN is grounded, then we go to the search stage, looking for the most likely world, which is performed by our GPU sat lib, and together with the maxboxsat CPU solver, which is what I told you that we both use the GPU and the CPU at the same time. Here it's easier to see this on the diagram. Toffee loads the evidence to Postgres, does the translation of clauses to data log, sends the clauses to JAP Prolog, which further translates them into a numeric representation so that it can be understood on the GPU. And then GPU data log performs the grounding, reads the evidence from the database, performs the grounding, and writes the results back to the database. And this is the first part of the grounding, computing the active atoms that are going to be used on the search stage. And then we continue with computing the active clauses, which is a similar process. The clauses are again translated, sent to GPU data log, and are grounded. And then we go to the search phase. We create and partition the Markov random field, and then we solve. Toffee is in charge of solving the smaller parts on the CPU, and at the same time, the larger parts of the Markov random field are solved by the GPU. And finally, we have our most likely world and display the results. GPU Toffee is also capable of weight learning, and like in the inference process, the formulas are first grounded using GPU data log. Then the initial value of the weights is proposed, and we do the optimization using the diagonal Newton method. The idea of the diagonal Newton method is to move to the solution, to the optimum value of the weights, by calculating new points based on a step size and on the gradient of and the Hessian of the formula for the weights. And this gradient and Hessian are approximated by performing the sampling, with this algorithm that is called MCSAT, which itself calls GPU sample sat, which is included into our GPU sat lib. And that is to count the number of times a predicate is true to find the Hessian and the gradient. And well, here we have the diagram of how this is done. We first ground, then created the Markov random field, propose an initial value of the weight. And we use here the whole Markov random field, that there is no opportunity to partition here. We sample this Markov random field, find the truth values, and with it we can update the parameters of the diagonal Newton method. The diagonal Newton proposes a new value for the weight, and we repeat this process with the new values for the weight until we have the optimum and we can display the results. Now our other platform is called GPU Rocket. This one is based on solving the inference problem as an optimization problem. As I said, the ground predicates represent variables and the formulas represent restrictions to the problem. We had to add around 500 lines of Java code into Rocket. Its main components are Rocket, MySQL, JAP Prolog again, GPU data log, and the Groby optimizer to solve the optimization problem. Well, GPU data log, along with JAP, are the ones in charge of performing the grounding process, and Rocket is in charge of any pre-processing, uploading into the database, and in charge of calling the Groby optimizer to solve the optimization problem. And here, as we can see, it's similar. The grounding process is similar. We also load the evidence, we translate the clauses, and we perform the grounding with GPU data log. And now the thing is that this grounding adds new restrictions to the problem and allows us to solve an initial optimization problem that would allow us to continue performing the grounding, to find more restrictions to the problem, which are added to the problem. The problem is again solved, and we continue adding these restrictions until there are no restrictions, and we have, well, until we have added all restrictions, and we have the final optimization problem that will give us the result. Well, we performed an evaluation of both of our systems using these 6 applications, and here we can see the number of tuples in the relationship and the relationships and the formulas. And well, first, the performance of our max-Walksat algorithm on GPU. What we did to compare its performance was to compare versus GPU Toffee, its normal version that only includes grounding, against a version of GPU Toffee that includes both grounding and search. And what we found is that our max-Walksat algorithm is very good. It's always faster. Well, this GS GPU Toffee is always faster than G GPU Toffee for applications that use the solver. Not all applications can use the GPU solver because some applications have a very small Markov random field, and it is not convenient to send to use the GPU to solve the search problem on. Well, the result was that it produces better results in a lower amount of time. How we know that it produces better results? Well, we have something called the cost, which is computed as the sum of the weights of all unsatisfied clauses. That means that if we have a clause that weights 1 and it's unresolved, then we add it to the cost. Then we have another clause that weights 3 that is unresolved, we add it to the cost. And we have 4 already on the cost. The idea is that the cost is 0. That would be that we found the best solution. It is not always possible because there can be contradictions in the data, and when we find contradictions, we will never reach 0 on the cost. But the idea is to find the minimum value for the cost. Well, as we can see here, for some problems, we found a much better cost in a lower amount of time. And even here that we both found the same cost, well, it was found on a much lower amount of time. Now, the performance of our GPU Rocket system, it was compared against Rocket. We performed very well in 3 of the applications, but unfortunately we were unable to find to provide a significant speed up on the other applications. What we found from analyzing our results is that some grounding iterations on these problems that made well are very large, so they greatly benefit from GPU processing. But the problem is that others are small, and well, the database and the GPU input-output times greatly reduce the benefit of the GPU processing. And now about weight learning. Well, since it also involves grounding, we again had to compare using the grounding on GPU Toffee. Otherwise, and then using Toffee's sample SAT solver and our GPU solver. Because if we use Toffee without parallel grounding, then Toffee would be simply stuck grounding, and we would never be able to evaluate our sampling algorithm. Well, we did very well in the first 3 applications, but unfortunately not so much in the other 2. What we found from our analysis is that for these 2 applications are relatively small, and the low number of atoms and the flip strategy that it uses adversely affected. Why? Because we are stuck in a series of middle solutions, because some threads on the GPU try to push to a better solution that is are computing max Walksat step, but others try to sample around the solution. That is, they are computing a sample SAT step, and we get stuck between them in a middle solution that is difficult to advance. But, well, as we can see, also the time is reduced. And, well, in this case, moreover important than the time is that the solution cost is much better, at least for these two applications. Now, finally, our contributions. Well, we have parallel algorithms and designs for all phases of the MLN processing. Our GPU data log, our GPU SAT library, our ILP system, our GPU Toffee platform, and our GPU Rocket platform. So in conclusion, these designs and the platforms themselves are the first massively parallel GPU-based MLN processing infrastructure. The core components are also a first massively parallel GPU-based solution for their specific applications. That is, GPU data log is the first platform to process data log on GPUs. Well, the performance of our platforms was on par or better than that of Rocket. Currently, it is the fastest CPU-based system. And well, the core components of our platforms, that is GPU data log, GPU SAT lib, have also very good speedups and can be used not only for MLNs but for general data log applications, for general sampling or SAT solving applications. Well, there's future work in several directions. For example, for GPU data log, its performance could be increased with transformations to the first order logic rules like counting or magic sets. I'm going to show you an example. Or by using a hybrid CPU-GPU approach where the idea is to have rules being processed both by the CPU and the GPU at the same time. Here we have a small example of what I'm talking about with magic sets. Imagine that we have again the grandfather example. Now we have four evidence predicates that would lead to, that would lead to two solutions, right? Because the grandfather of Bob is going to be Peter, and the grandfather of Fred is going to be Frank. But we are only interested in who the grandfather of Bob is. If we evaluate this rule normally, using the bottom-up approach upon which GPU data log is based, then we are going to find both solutions, both Bob and Peter and Fred and Jack. And then, once we found the solution, we simply prune this solution to give Bob Peter as the solution we are looking for. But as you can see, we have already computed an additional solution that is not useful to us. So the idea of the magic set is to put an additional predicate or a series of additional predicates that try to guide the solution to what we want from the beginning. So by putting here the Bob as a constant, then we force y to take only one value, which be John. And that would allow us here, if we only can have John, then we will have Bob for x. And if we can only have John here in y, then we will have Peter for z. And the result of this clause is going to be Bob Peter only. And we never consider these other two predicates. So as you can see, it's quite efficient, and it doesn't really need any changes upon the GPU data log engine, only on the preprocessing when we're going to give the rules to GPU data. It can also be extended with load balancing and network communication. The idea is that we could use a cluster of heterogeneous GPUs, that is a cluster that has GPUs, not the same kind of GPU, but of several different kinds, which would also be very nice for big data. Then our parallel ILP system has to handle MLN, close learning. And as I said, that can be done by changing the function from coverage to an MLN-specific function. And then general improvement to ILP is the use of coverage lists to improve its performance. Coverage lists are very simple. Imagine that we have proposed this rule, and we compute the join here, and then the join here. But then we have a new rule that has this one, and then a different predicate. Instead of P3, has P4. So normally we would have to compute everything again, this join, and then this join here. But if we store the results of this join in memory, then we would not need to compute it again. We would simply use its result and then join with the new predicate that we are proposing. GPU Toffee would benefit from the removal of the database manager of Postgres, because right now it's only in charge of communication. It doesn't really serve the same function as it did on normal Toffee. And also the partitioning problem on the Markov random field is complicated. It could be used, the GPU could be used to solve it. Here we have a very small example, but it's the same general idea. The Markov random field represents a graph, and the graph usually has non-connected components or weakly connected components. And the idea is to find the non-connected components and the weakly connected components to perform the partition. But in a graph with millions of nodes and vertex, it's a very difficult problem. And finally, for GPU Rocket, well, we could change the solver that is currently using to solve the optimization problem. It could be based on GPUs. It could perhaps be a meta-heuristic. Here we have the common algorithm to perform a simple meta-heuristic based on a population with individuals, mutating and crossovering these individuals, evaluating them until we have found the solution to the problem. These individuals represent the solution to the problem. Well, these are the publications we have, and that's it. Any questions?
So how's the round going to be?
Yes, we begin.
Yeah?
I'm going to move the camera again, Ines. You can start with the questions. We can't hear you.
Can you hear me?
Yeah, now we can. Thank you.
Carlos, thank you very much for your presentation.
Thank you, Ines.
I would like to compliment everyone in the audience and also Dr. María. I don't know if is Jorge there?
No, I'm afraid not, Ines. I sent her the invitation, but well, I don't know.
He couldn't make it. Okay. Right. So I would like to compliment everyone in the audience. Thank you very much for giving me the opportunity to be here. I liked a lot your presentation, Carlos. You were very clear, and everything. I mean, I had already read your thesis, of course, and had sent you also some comments about the text. So to start with, I think I should first say that you did quite a lot of work, and it's a great body of lots of things. You touched lots of things, and you had to learn about Prolog and all the probabilistic stuff related to MLMs, and you also touched on things related to statistical also to optimization algorithms. So it was a great challenge, and I think you did very well with your work. You have very good implementations and very good contribution. I have some questions. I won't be very long. I will just ask some questions, very generic ones. The first thing I wanted to ask is regarding your GPU data log implementation, where you can use GPU data log to do coverage in NLP.
Yeah.
do you think that you would have any problems or any difficulties, or there is no difference if you had to deal with concepts that involve multiple variables in the head of the clause? Because in NLP, usually, I think that the examples that you had to deal with, all of the learning was done on, all of the learning was done on concepts that were using only one variable. So if I added multiple variables to the concept, do you think that this would make any difference and to your coverage step on your when you do that on GPUs? Because I know that you convert all of your clauses to numerical formats in order to ship them to the GPU to execute all of the clauses on top of the example. So my question is, if the examples have multiple variables, would this make any difference?
Well, I think it would only make the coverage process to take longer, but I think there shouldn't be any problem. Maybe there would be a problem if the head was negative or with handling negation there, but in general, increasing the number of variables in either the head or the predicates shouldn't be a problem, and the ILP system should be able to handle it.
Okay, so my second question is related to scalability. You ran benchmarks for all of your systems on the GPU and on also using the help of multi-cores, and they have different sizes, right? But did you evaluate any one of these data sets with increasing data set size? What I mean is, did you get one single data set and did an evaluation of scalability for just one thing? I mean, taking a sample of one data set and then a second sample is slightly bigger and then another one slightly bigger. How do you think that your systems will behave if you increase the data sets?
Yeah.
Because I know that tell me.
Sure. Well, I tried it with a smokers example, increasing the size of the dataset, but I was using random data, and well, it's a bit difficult to measure because I don't know how deep the recursion of this is going to be. Because, for example, in the smoker example, because it is recursive, I could generate a data set with, let's say, 10 smokers, but it will maybe grow to 100 as a result. Or I could have a data set that has already 100 smokers, and the result would be only 10 or something like that, because I don't know. Because it is the friend of friends is also friends, so you increase the size of the friendship relationship, and at the end you don't know how many friends you are going to end with from the beginning of the data. So it is a bit difficult, but in general, the greater the data we have to process, the better the performance of the algorithm. But the main problem is that we can run out of memory, and sometimes we cannot know beforehand if we are going to run out of memory or not with a certain problem. That's why we created the partitioning scheme, that it allows to partition the data in sizes that we know that even if we reach the worst case scenario for a join, which would be the Cartesian product, we can track back and perform again the operation, always having enough space to store the solution. And that way, well, I hope that the scalability has grown to any data size. We still haven't done definite tests to it, because with handling big data we find some additional problems. For example, this conversion from strings to numbers takes a very long time. Then all the input-output between the database, between MySQL and Postgres, it also starts to take a very long time. So, well, there are still a few things that we need to solve about this partitioning problem, but I think that is the one that is going to give us the most scalable solution.
Okay, that's food for a new PhD, right?
Yeah, maybe a postdoc.
Yeah, so, Carlos, do you have your implementations available somewhere that we can access and can use? I have your version of GPU data log for the app. I'm waiting that the app gets to a point where I can use it again, because Victor is still working on a new version. So do you have your implementations available that we can access and can do some other work? Because I have many students here that would be interested in using some of your work to extent.
Yeah, right now only GPU data log is available. I need to talk to Dr. Peter about it, if we are going to upload it to his account, to the account of the University of Porto, or which could be the best place, and also if we should also put all of Toffee's code along with my implementation, or only the files that I changed from Toffee. I have people download Toffee from the official Toffee webpage, and then download my project from our webpage, and that's it. But in the meantime, I can send them to you so that you can have them, and for anybody else who is interested in my work, you can give me your email address and I can send it to you, my implementations. All you need is GPU, otherwise it's not going to work.
Okay, Carlos. I have interacted a lot with you before, so I think I asked you everything that I wanted. I think you did a very great work, and yeah, congratulations to you and your supervisors. I enjoyed it. Thank you very much.
Thank you, Ines. No. Dr.
So,
Peter?
do you want to move to Peter?
Yeah?
Hello, Carlos, how are you doing?
Hi, Doctor. Fine, thank you.
So it's a really great pleasure for me to be here today.
Yeah.
Here, graduating.
Yeah.
I'd like to say my compliments to people at the Universidad,
Thank you.
Professor María, to everyone else for supporting you and helping you improving your thesis. It was really quite a bit while we were there. I think that's partly thanks to María, Doctoral María, and also I think you also collaborated with Jorge, right?
Yeah. It was unfortunate that he could not join us, but it was very nice working with him.
Yes. So my compliments go to Jorge as well, because
Well, we need to do a Skype meeting with him some other time to catch up.
or even we go.
Yeah.
And then maybe with Manchester.
It would be a bit difficult to me, but it would be very nice.
Definitely. So I'd like to start by that. And also your work. I think it's great work. I really respect it. Just as English said, we started from scratch. We really didn't know much about relational systems, induction, machine learning, all stuff. So
It's almost done, right?
It's almost done for me, yes. Well, definitely.
Great.
Please. So we can talk about it later, we can organize a meeting about it.
Sure.
It's actually almost done.
Sure, sure.
And lots of questions. I think Asia asked the really important ones, obviously. But I would like to ask one or two questions too, if there is time.
Sure.
And my first question is, imagine that you are presenting your system to someone else, who's using Buenabad. What are you going to tell him? To speed up Buenabad by a factor of something. Can you describe the performance of your system in one or two phrases?
Well, I would say that it is very useful system to perform several statistical relational learning tasks like classification.
Why is it so useful? Purpose sequential system.
Well, because it is faster and produces better results than other systems that currently exist in the market.
Can you give for that, give it a number, process number?
Process the number?
A number. It would be 10 times faster with the best.
Oh, all right, right. Yeah. Well, the thing is that it is, for example, compared to, for some applications, it is more than 100 times faster because some applications are very good for it, and other times it has a similar performance. So I don't know. Maybe I could say that that it is 100 times faster on some applications, and maybe that would be very nice. Just for others, it would not have that much of a speed up.
Anything special about those applications that you say so that you would be used to?
There are applications that have a lot of data and very deep recursions. I think the key part in that is that very deep recursion works very well with GPUs.
Because it's the same thing over and over again, right?
Yes, exactly.
So that's where you expect more gain, and that's where you expect analysis to go slower by nature. This question.
Yes, yes, exactly.
I would say that your system would gain the most when analysis is the slowest.
Yeah.
So I think that's something that you might want to consider having in a thesis, or maybe we try to submit it later. If you give a statement, not exactly what you reached, a lot. There is some small synthesis. Just one or two phrases would make it. I think that's a little bit missing in your thesis, saying that you can reach about 200 times speed up on some configurations, but I benefit from deep recursion.
Yeah.
That's something that's really important.
Yeah, it's something that we definitely need to add to the paper that we are due to publish.
Hopefully, and I think we should talk about it.
Yeah.
Sooner than that. That's something that I was listening to your presentation about the. One question, usually when people do the growing optimization people, there's a professor here who works a lot with people in Japan, doesn't know. And they say that basically technical R stuff Do you think you can overcome that?
Yeah, well,
Because we do, my understanding is that it's split into different, the problem solver is done by sequentially, right?
sorry, the what?
When you do the optimized implementation, there's a step which is done by the solver.
Yeah, the SAT solver.
Okay, but then when is the Ruby solver used, actually?
The what?
Ruby. Japanese solver.
Oh, right. On GPU Toffee, on GPU Rocket, I mean, is used along with the grounding. You do the grounding, solve an optimization problem, then you ground again, solve again, and it's so forth a loop between them until you reach the solution.
But when you do that optimization problem, you basically running sequentially, you not do it with GPU. Okay.
I think it might be possible. There are already some algorithms to perform optimization on GPUs. So it would be a matter of checking if we can adapt one to our needs.
Yes.
Or create one from scratch, which would also be nice.
Yeah, that would be cool.
That is really nice.
So, that's what I was asking, whether you feel that that's possible to do or not.
Yeah.
How much time so all the benefits you can have from the grounding is limited by the amount of time spent solving the optimization problem. Right?
Well, for some problems, the grounding is very fast, and that was the problem that we had with the 3 applications on GPU Rocket, because the grounding was a lot of groundings, but very small. So we were having problem with MySQL, the input-output time, and also the input-output time between the GPU and the CPU. So, but on larger problems, the grounding is big, and sometimes the optimization problem is even bigger. There was one of the problems, I think it was entity resolution, that the current error, the gap that has on Groovy by default, it was too small and it was not reaching any solution. It was just stuck trying to find the best solution, and it was not finishing. So we actually had to increase the value of this gap so that it could finish and give us a solution. So, well, from that example at least, it is clear that the solver can be, well, there's room for improvement on the solver, and I definitely think that GPUs could be a very good alternative to what Groovy is doing. Especially also since Groovy is not open source. There are academic licenses for it, but if you want to use it outside the academic environment or something like that, well, you are out of luck. You need to buy it.
Yes. That solved as a constraint problem, but again, it's part. There are also parallel constraint solvers and GPU-based also.
Yeah, Groovy uses the barrier method and the simplex method to solve this optimization problem. So I think it might be possible to adapt these algorithms for GPUs if they are not already adapted, or use maybe a meta heuristic, which is, at least it sounds easier to parallelize because you have your population, the individuals, and you could evaluate them in parallel. So there, it's possible that we could have some.
It's a nice idea, I think, because then you use that as a virtue. Right, the different components of the system in this service.
Yeah.
Okay. I was trying to say that it's a good idea because it can reuse it. It can use it for other problems.
Yeah, and another paper.
Yeah. The other question you talked about is that when you do the dot solving, sometimes you get stuck around the solution. Right? You don't converge.
Yeah.
Is that because you are switching to many points at the same time?
Yeah, the thing is that there is a certain probability that a core performs a max walk-sat step, and those are the steps that flip the right atoms, so that we can reduce the number of unsatisfied clauses. But then there is also a probability that it performs a sample sat step that is in charge of sampling around the solution we are. And to do this sampling around the solution, it flips any atom. So it is possible that it flips a critical atom, especially since there are several cores flipping multiple atoms. And then we worsen our solution. And then at the next iteration, we improve it, then we worsen it, and thus we get stuck in a middle solution. To solve that problem, well, we would need to talk about it. Perhaps to have one iteration perform mag walk sat, then to perform the sample sat to iterate, and then continue with mag walk sat, so that we can be advancing and sampling, It might be.
I was thinking that what you're talking about today, sometimes it reminds me a little bit of simulated annealing.
Yes, that's the algorithm.
Then what people usually do is annealing is they reduce the growth. So in this case, it is flipping less pieces in red post.
All right, the cooling part or something like that, right?
Yeah.
So that would be exactly the cooling part. So the process solution probably wants to have less pieces. That would mean that you don't want to jump around as much.
Yeah.
Might help a little bit.
We would just need to define how to perform the cooling on MLNs. Maybe it depends on the problem or on the number of atoms and clauses that it has. But yeah, it would be a very nice improvement.
And I don't want to take much time, but one last question. So when we started, there was the state of the art in terms of GPUs and databases using GPUs and time operations, and got to read a lot of papers about those things. Do you think that the state of the art evolved a lot since then, or are they still the same algorithms? And related to that, do you think right now that we could move to the data language, OpenCL, or whether we should still keep the promises still need to use?
Well, I haven't checked the latest on OpenCL. The time I was there, that was in this conference, BECPAR, the people from AMD told us that they were really expanding upon OpenCL, and that soon we would have the same algorithms that we currently have on CUDA, or an equivalent. There was also this tool that converted the CUDA code into OpenCL, and I actually managed to convert the code to OpenCL, but there were these functions that were currently not implemented on OpenCL, for example, to perform the scan operations and so forth. We need to check, I need to check the latest about OpenCL to see if these functions are already implemented, and then we can move to OpenCL, because Well, we would also need to measure the performance, but I think it would also be a very good performance, and we would also be able to reach much more hardware than we currently reach, because we only can use, currently we can only use GPUs from NVIDIA, and that really limits the...
But they dominate anyways. They have more than half of the market now.
Yeah.
Although with the FCL, you probably can use Intel CPUs also.
The what?
Intel,
Oh, yeah. Yeah, yeah.
not just CPUs, but these parallel machines that they have. Not very popular.
Well, but it would be nice to look into it, to see what else we can do.
Because there are MLMs in Android machines.
Oh, yeah.
Android machines too.
To perform MLM processing on the go.
Right now.
Oh, yeah.
I think this is the presentation was pretty good. I would like to see some more color, to be honest. But, I think it was more well organized. The things that have to be mentioned. It's difficult because there's so many things to sometimes keep track, but they did a pretty good job of that. I think you improved a lot of the introduction. Yeah, the introduction is much clearer now. I still think that some of the figures are a little bit complicated.
Okay.
The personal opinion, of course.
No, I'll try to improve. Sure.
Yeah, so we can talk about that in more detail.
Good. Yeah.
I think that the result section is also much more clear oriented towards its target. But partly my fault that I couldn't do the original results again, so I cannot complain about that.
No, well, but we can still do them for paper and so forth.
Yeah, I think so. That I think there's also, as you mentioned, part of negation. So you're just doing stratified negation.
Something similar is, well, right now I am defining it as a set difference only. So we leave the stratified negation a bit to the side, but maybe it would be nice to check what would be the best kind of negation for MLNs. Right now, negation as a set difference works well, but maybe if we want to do something more complicated, like negation on the head of the predicates or on the head of rules or things like that, I think we are going to need some more sophisticated kind of negation.
Interesting. The work might be applied to ASPs, so answer set programming. Because in the sense that's what they do grounding, and they do tussle.
Okay.
They already have one trading. So in that case, it doesn't really matter to you very much that it's negation or not, because they simplify the program to be the original one. They remove the negations first and to the grounding, and then they apply the conditions later. So I understand it works. But that would be something really interesting, and I think it would be easy for you to do with the technology that you do.
Yeah, I'm also going to look into it. It sounds very interesting.
Yeah. I think otherwise, negation is complicated because of loops negation. So predicates meaning depends on the negation of the meaning. It depends on that being false.
Okay.
That's the basis. That's a big problem. That's one reason why people don't like this very much for complex programs. I'm also impressed that you've been doing negation. That's really cool. also, of course, we might connect it to the app and to the top level part, so we could have both top down and bottom up people at the time.
Yeah, yeah, with GPU data log, yeah, it would be very nice addition to yeah.
And we should talk about that.
Sure. Okay.
Okay, so I don't want to take too much of your time. Thank you very much, Carlos. Just quite a lot.
Thank you, Doctor.
And I think you were doing great work.
Thank you, Doctor.
But I would like to join my colleagues for congratulating you. You have done a very good job, and I enjoy reading your thesis thoroughly. I must admit that from time to time it was very hard work doing so, because you cover quite a lot of material. You have told us and explained you several strategies for parallelizing a number of algorithms. And in your results section, for example, you show some applications for which your platform outperforms others. My questions are also going to